32 are graphing exponential equations. These were both actually exponential decay because we have a 1/2, so a number smaller than 1. We know when we graph exponential, the graphs go through 3 points. The parent function goes through 3 points. It goes through the point 0, 1, 1b, and -1, the reciprocal of b, or 1 over b. Remember, reciprocal is just, or 1 over b is the reciprocal. Just put a period there, reciprocal. Parent function means there's nothing added or subtracted up here or outside or something multiplied here. So this is a parent function. So we can graph the point 0, 1. We can graph the point 1b. So in this case, in our specific graph, we want 0, 1. 1b, b is the base, so 1, 1/2. And -1, the reciprocal of b, the reciprocal of 1/2 is 2. So we'll graph those few points. We got the point 1, 1/2, and the point -1, 2. If you continue to put a couple other points in here, you would get -2, 4, and -3, 8. And so this would be graphed coming down through here. And then we have this horizontal asymptote at the x-axis, and that happens always with exponential functions, that you'll have a horizontal asymptote. So there's those 3 points, or those 3 points, and then there's the graph. Now, these are actually related because this is 1/2 to a power, but how's this one going to be affected? Well, it's going to move left 2 and up 2. So we're going to start with these same few points from the parent function. We'll start with this graph, and then we'll do our shifting of points. So we've got 1, 0, 1, 1/2, and 2, 4. And again, we could have put a couple other points in here if that's helpful. And now in red, my final graph is going to be in red. It's going to go left 2 and up 2. So this point's going to go left 2, up 2. This point here is going to go left 2, up 2. This point, left 2, up 2. And a couple other ones. So you hopefully see this graph taking shape as we move everything up 2 and left 2. Also, we usually had an asymptote here on the x-axis. It's going to move up 2 and left 2. Well, the left 2 doesn't really mean anything for us, but it is going to move up 2. So the asymptote I'm going to put as a dotted line here. Moves there, and then we can draw the graph of this function, hopefully. It's going to come and have a horizontal asymptote. It's going to get closer and closer to that line, but never reach it. Still a pretty sorry looking graph, but the important points there are for you. Graph the points and then of the parent function, and then shift as necessary. All right, jumping into logarithms, we are starting with our rules of logarithms. So this test is a little bit backwards because later we'll convert from logarithmic to exponential form. But expand each logarithm. First, we want to deal with this 5. There's actually 2 ways to do this. If there's a 5 out here or an exponent out here, I would first move it to inside here using the rule of exponents. So log base 4 of 3 to the 25th, because you do 5 times 5, times 5 to the 5th. So that's just a rule of exponents. But now we can look at the rule of logarithms, and we have a logarithm of a product. We can split that up into 2 individual logarithms that are added together. So 3 to the 25th. So when multiplying, we can change it to addition of log base 4. It's supposed to be a 4 of 5 to the 5th. And then we had the power rule that we talked about, which means we can move these two exponents out front. That'll come out front there. And so our answer is 25 log base 4 of 3 plus the 5 comes out front, so 5 log base 4 of 5. And there's our answer for that one. Over here, we're still expanding, but now we have division. There's no exponents on the entire outside to work with, so we don't have to do anything with that. And so we know that division of logarithms can be changed to logarithm of the numerator minus the logarithm of the denominator, as long as they're the same, and we make them the same base as the original. So 7 to the 5th. And then once again, we'll be able to use this power rule where these come up front, and we call this will be 2 log base 4 of 2 minus 5, because the 5 comes out front, log base 4 of 7. And that's it for number 34. 35 and 36 are actually the reverse of what we just did. We expanded in 33 and 34. Now we're going to condense, so we're actually kind of starting with something like this and moving backwards. So the first thing we need to do is move any numbers multiplied, any coefficients, we move them to the exponent, which there's just one in this one. So we have log base 8 of A plus log base 8 of B plus log base 8 of C to the 5th. So that 5 comes out front, and now we have several logarithms added together. Well, we can combine that to a single logarithm, and we can multiply the 3 different numbers we have here. So we have A, B, C to the 5th. And that is our condensed version. Same idea here. These numbers will need to come up first into the exponent. So we have log base 6 of 7 to the 4th minus log base 6 of 8 cubed, and subtraction of 2 logarithms with the same base we can change to division into a single logarithm of those 2 things divided. So 7 to the 4th over 8 cubed, and you can leave it like that. You don't need to multiply out 7 to the 4th or 8 cubed. All right, solve each equation. These two are set up nicely. They're kind of special because 16 and 2 can be written as the same base. Like we can factor down 16 to 2 to a power. So 16 is 4 times 4, and then each of these 4s is a 2 times 2. And so 16 is actually 2 to the 4th. And so what we do over here is we change 16, and we're going to say that's 2 to the 4th to the negative 3n equals 2 to the 6th. We're going to use our rules of exponents over here. So a power to a power you multiply. So this is 2 to the negative 12n equals 2 to the 6th. And when we have 2 powers with the same base, 2 to the negative 12n equals 2 to the 6th, we know that these exponents must be equal to each other. So 12n equals 6, dividing both sides by negative 12, we get n equals negative half. That's our answer for 37. 38, 27, we're going to factor this down. This is 9 times 3, and 9 is 3 times 3. So 27 is actually just 3 cubed. And 81 is 9 times 9, which is actually going to give us 3 to the 4th. So they both can be factored down to 3 to a power. So 27 is 3 cubed to the n. So we're just taking out 27 and putting in 3 cubed. 81, we're taking out 81 and putting 3 to the 4th. and that's raised to the 2n plus 2. We have a power raised to a power, so this is 3 to the 3n equals 3 to the 8n plus 8, because we're going to multiply the exponents. And once again, we have the same base, so we can just write that the exponents are equal to each other. And we're going to solve. We'll subtract 8n from both sides. And we get negative 5n equals 8. Dividing both sides by negative 5 gives us negative 8/5. So n equals negative 8 over 5. And there's our answer for that one. Here's where I was talking about before. We probably should have put these questions earlier on the test, but this is just rewriting or changing to exponential form. Remember, when there's not a base written here, it's a understood 10. So if you see a logarithm with no base, it's an understood 10. And so remember what we do. The base of the logarithm is the base of the exponent. So we're going to put it in exponential form. So it's 10. That goes here. To the negative 3 equals this number right here, 1/1000th. Over here, this is going to be similar. So the base 2 to the negative 2 equals 1/4. Going back the other direction, we're starting with an exponent. 1/2 to the second equals 1/4. So thinking backwards, the base of the exponent will be the base of the logarithm. So log base 1/2 of 1/4 is equal to 2. And over here, log base 20 of 400 equals 2.